Um, today's topic. Yeah. Continue on bisection method and topic one. Topics. Section B1 bisection method and section B2. Newton's method. Both these two methods for the solution of a single equation. At the end of the last class, I tried to present the algorithm for bisection method. But I think you can take a look at the algorithm at home. Okay, I'm not going to present the algorithm. But here, let me show you some properties about bisection methods and two examples. First example, actually, bisection method is quite slow, not fast. Take a look at this example. Use bisection method to solve this equation. This equation has a solution or a root or a zero in solve this equation in this interval. Okay, now take a review about bisection method by using these examples. The first column for iteration. First iteration starting with this interval 4 to 3. Second column, midpoint. We use midpoint as estimate of the solution of the equation. Midpoint is 3.1. This is iteration one. First step. Function value and the midpoint is negative 32. 1 point. Okay. So yeah, function value is C. Not small. But this is a step one. Step two. Yeah. Level 4. Level 3. Now midpoint. Function value and 4 is negative. Function value and 3 positive. Then function value at the midpoint negative. So the solution, the root, okay, root out. The root of this equation is in this interval. So step 2, cut this interval in half. Then the midpoint is 3.25. Function value. Function value is C. Okay. Yeah. So cut. This is a negative 3.25. Function value negative. Negative. So the root is in this interval. Now step 3. Cut this interval in half. Number step 3. Okay. Cut in half. Function value at the midpoint. Yeah. Yeah. Function value is decreasing, but very slowly. Very slowly. This is yeah, here. Positive. Yeah, positive. At this midpoint is negative 3, 1, 2, 5. This is step 3. Now, step 4. Step 4. Now, solution of this equation is in this interval. Okay, is in function value negative, positive, function continuous. So guarantee there is a solution in this interval. Now, step 4. Cut this interval in half. The midpoint is negative 3, 1, 8, 7, 5. Function value. Yeah. Function value is larger than the function value in previous step. Okay, continue. 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 When k is 15, the midpoint negative 3.1, 83, 1. Function value is negative 0.124. Step 16. 1831. Right. Yeah. Step 16 and step 15. The solutions almost no improvement, right? The solution at 16, step 16 has no improvement on solution on 15. So we stop at 16. The function value is 4, 5. Okay. So we stop because of no improvement, right? So we stop. This is a bisection. Yeah. Actually, quite slow. Bisection method just a convergence rate, just linear. Newton's method very fast. Convergence rate is the conjecture. Right. How to see convergence rate is linear. Yeah. Yeah. Here, suppose at step K we have AK, BK, this interval. Midpoint here, CK. Yeah. R root of equation. Maybe here. So CK minus R. Yeah, distance. Distance. Less than or equal to 1/2 BK minus AK. BK minus. Roughly, okay? Roughly. Yeah, the following argument is not proof. It's not a proof. Okay? Proof should be rigorous. Okay, should be rigorous. But for the following roughly, we can write CK minus R is roughly, okay, roughly 1/2 some alpha constant, okay, where alpha between 0 and 1 constant, okay, some constant. Right. Now, bisection method convergence is just linear. Take a review about linear convergence. A sequence converges some number x star. The convergence rate, how fast this convergence is, okay? The convergence rate is linear. That means that it's linear and approaches infinity. Xm plus 1 minus xn, okay? Yeah, over approaches some number, the number between 0 and 1. Okay? That if this limit is satisfied, we say that is sequence how fast to x star linear. If denominator is square, then the convergence how fast? Quadratic, order 2. Yeah, bisection method is just order 1. Slow, okay, not fast. Yeah. Okay, now I use this approximation. Now let me compute this limit. Yeah. Okay. CK plus 1 minus R as absolute value. Then over CK minus R absolute value. Roughly is 1/2 alpha. Okay. CK plus 1 is the midpoint of AK plus 1 to BK plus 1. So this is the BK plus 1 minus A plus 1. Then over, yeah, 1/2 alpha BK AK. Right, now we can cancel out 1/2, cancel out. BK plus 1 minus AK plus 1, it is the length of the interval next step. Okay. Every step we cut interval in half. So this quotient should be 1/2. Yeah, 1/2. Yeah. The length of the interval next step is 1/2 of the length of the interval current step. So for any case, roughly is ratio is 1/2. So the limit is 1. Yeah. Roughly bisection method convergence. How fast? Linear, so fast. All right. Next, it is a theorem, but this theorem very makes sense. Not hard. Yeah. Okay. A theorem on bisection method. Then A0, B0. Yeah. Initial interval. Well, we start with this interval. Then step one. After step one, we have this interval. After step two, we have this interval, and so on. Each interval contains a root. Then R be the root or zero of this equation. Contained by these intervals. Every step, bisection method generates an interval. The interval contains a root. Not that. Yeah, very easy. Okay. Then AK, yeah, left endpoint of these intervals will approach out. Of course, Y endpoint also approaches out. B point, of course, approaches out. Yeah, C, B point approaches out. Step two. How close the midpoint of an interval is from the root? How close? Yeah. R minus C, K, less than or equal to negative K plus 1. Right? Then B0 minus this. Okay, now let me use this inequality to answer some questions. Okay, example 2. Suppose that the bisection method is started with this interval 50, 63. Yeah. A0, B0 is this interval. Now the question is, how many steps should be taken in bisection method? Should be taken to compute a root with relative error or relative accuracy of 10 to negative 12. Yeah. That means that determine K. Yeah, K, step number. Determine K. Such that CK, CK, the midpoint of an interval. CK minus root, absolute value. This is the error of CK from the root. relative, okay, relative accuracy, yeah, relative to the rule. Determine K so that the relative error is less than this. This is the question. What K can make this inequality true? Now, to answer this question, because the intervals contains R, okay? Initial interval contains R, okay? Because since R is in this interval, we assume okay, R in the interval. So therefore, so CK minus R, yeah, log greater than what? R is in this interval, so log greater than CK minus R. 50, you agree? Okay, now, in order that this inequality is true, I make, okay, this quotient less than, yeah. If this quotient is true, then this is true. Because of this less than. So now I solve this inequality. Okay. Okay, now find the result here. Find the result here. Okay. Yeah, find the result here. So I further have I want to solve this inequality for K, but not solvable. Why? Because I don't know CK, but let me use this. R minus CK over 50 less than or equal to 2 negative K plus 1. Then B0 minus AC over 50. Okay, now I set the right side less than 10 to negative 12. If this is true, then this is true. Then this is true. But this inequality is solvable. We can determine K in this inequality. The other inequality is not solvable. Okay. Now let me solve. What is B0 initial interval? 63. A0 50. So this is 63 minus 13. Okay, 63 minus 50. Yeah, solve this inequality. All right, now solve it. 2K plus 1 times 13 over 50 less than 10. Yeah. So the solution is K greater than or equal to 37. So we need to run 37, at least 37 steps to guarantee the midpoint and the root relative error. Okay, this is a Bisection method. Now second topic, Newton's method. Topic 2. the Newton's method. Newton's method also a method for the solution of solve. Yeah, solve is so bisection method also solve this. Right. Now let me plot graph of function n. Right. Function n. Suppose the graph is this graph. Then solution of the equation is here. This is the R. Now we want to find R. Take a point. Take a point. Yeah. Near R. Take a point. Okay. Take A0. Then on the graph, we have a point. This point is x0. Function value is x0. Yeah. From that point, draw a tangent line. Yeah. Draw a tangent line. Right. Tangent line. Suppose intersect x-axis at this point. This point we call it x1. Now x1 graphically x1 closer to the root than x2. After we have x1, then on the top, this point corresponds to x1. This point, x coordinate is x1, y coordinate is x1. And this new one, draw a tangent line. Draw a tangent line. Draw a tangent line. Okay? Draw a tangent line. Yeah. Tangent line intersect x-axis at this point. This point, call it x2. x2 closer to R. After we have x2, draw a tangent line at x2 to get x3. After we have x3, draw a tangent line to get x4. And so this is a Newton's. Graphically, the sequence converts to R very fast, very fast. Especially when the points near R converge super fast. All right, this is the idea behind. Now let me write down formula for Newton's method. Okay, Newton's method. Write down formula. Let me erase this side and the draw side. Graph of the function is an n. The root is here. Suppose we have obtained xk starting from x0, then we get x1, x2, x3. Suppose that we have a k, xk. Then on the curve, the corresponding point is xk, function value and xk. Now, to get xk plus 1, at that point, draw a tangent line. Draw a tangent line. Yeah. Tangent line intersect x at a point. This is a coordinate point, xk plus 1. What is the formula for xk plus 1? Okay. Yeah. The slope of this tangent line is derivative. Slope of tangent line is derivative. Derivative at xk. Yeah, slope. Yeah, slope. Hey, I have slope. Suppose I know xk. So I know slope and I have a point. So point slope formula, I can write down the equation of the tangent line. Yeah. The equation of the tangent line at the point sk f xk. Yeah. Yeah. Equation of this tangent line is point slope formula. Y minus y1. Y1. Yeah. Function is equal to slope derivative at sk. Parenthesis x minus x1 xk. Functional formula. Okay. Now I want to find out this point. Yeah, the point here. What is this? Okay. I want to find. At this point, y coordinate is 0, right? Because the line will hit x-axis at this point, y is 0. So, okay, now set y 0. Yeah, in this question, then we have this. X minus x. Now solve this for x. X is a point where the tangent line across x axis. Now the solution is this. Solution. So x coordinate of this point is this. Now this point is real approximation to the root. We call this point xk plus 1. Yeah. So xk plus 1 is xk minus f xk f. What is k? K start with 0. When k is 0, x0 initial approximation to the root. What is the initial approximation to the root? The initial approximation is from us. We arbitrate as initial. Of course, we assume the point close to the root. Yeah. So below x0. Now starting with x0, k is 0, we get k K1. We get X1. After we have X1, we have a plug in X1 on the right side, we get X2. After we have X2, half X2 on the right side, we get X2, and so on. Yeah. This iteration is called this iteration is the Newton's method. Newton's method for the solution of this equation. Okay, we continue with this topic. Friday. Right? We stop here. I have office hour tomorrow, Thursday, from 10 to 10:30. If you have questions, yeah, please ask. My office is 2K. Rush of 2K. You can find this information in